Okay, here we go on our penultimate unit of the year. We only have two left to go. This one is called linear momentum, and today's lesson is going to be on momentum and impulse. Let's get started. So, momentum is a word you've probably heard before. It's a word you've probably used before, although chances are you may not have used it correctly. It has very specific meaning in physics. So, basically, momentum is an aspect of an object's motion that is equally dependent on its mass and its velocity. So, the definition of momentum, which unfortunately we symbolize with letter P. I guess M was taken up by other things like mass. Um, so P is basically equal to mass times velocity. Momentum is mass times velocity. It's equally dependent on both. It's just the product of the two. So, for instance, if I have two objects traveling at the same velocity, but one of them has twice as much mass, it will have twice as much momentum. Similarly, I have two objects of equal mass. One of them is traveling twice as fast. It will have twice as much momentum. All right. Now, the most important thing to know about momentum probably is this, is that it is a vector quantity. And therefore, we have to keep its direction in mind when we're dealing with it. Remember, anytime we multiply a scalar like mass times a velocity like vector, we end up with a vector quantity. So since we have mass times velocity, it's going to be a vector. So what does that mean in terms of problem solving? Well, it means that when we look at a system of two or more objects, when we sum up the momentums, we have to take direction into account. So we have to just ascribe one direction to be the positive direction. If we don't have any other reason to do so, we should choose right to be the positive direction. So look at this here. I have two objects moving in the positive direction. One has the momentum p, one has momentum 2p. So the momentum of this two object system is 1 plus 2. It's 3p, 3 units of momentum. What are the units of momentum going to be? Well, it's mass times velocity. So the units are going to be kilogram meters per second. I mean, it's kind of an ugly unit, but that's what we've got. Well, let's look at this other system. Now I have the same thing, except this one's going in the opposite direction from before. But I have a very different amount of momentum in this system. So I have 1 unit of momentum in the positive direction, but I have 2 units of momentum in the negative direction. So p plus negative 2p gives me negative p. So this has 3 times less momentum and it's directed in the opposite direction. Now, impulse is a very related concept here. It's a very cool concept, as you'll see in a minute. And it may be something you haven't heard much about before. So, impulse, simply put, is the change in an object's momentum. All right. So, but if you think about it, how would I change an object's momentum? Well, I'm not going to change its mass. What I'm going to do is I'm going to change its velocity. In order to change the velocity of an object, I have to make it accelerate. Otherwise, it didn't change its velocity. In order to make something accelerate, you got it. I have to apply a force. Remember, F equals ma. So the idea is this: if I say F equals ma, all right, Newton's second law, and I say, well, I'm going to take A and I'm going to define it as the change in velocity over time, because that's what it is, then I quickly can derive the impulse equation, which is force times time is equal to mass times the change in velocity. Now, this, since if I change the velocity of a mass, I've changed the momentum. We often write it this way. Now, you'll notice sometimes, even in this particular screencast, sometimes I'll write m delta v, and sometimes I'll write delta mv. It means the same thing: it's change in momentum. So, in other words, a force applied over a given time is going to cause a certain amount of change in an object's momentum. Let's look at some of the implications of this. Okay, so in sports, it's pretty interesting how this comes into play. In many ways in our lives, it comes into play. We sort of understand this at a gut level, but I want you to understand it at an intellectual and physics level. So if you've taken baseball, soccer, pretty much any sport, your coach has told you how important it is to follow through, right? What that means is don't stop swinging the bat as soon as you make contact with the ball. Just keep your arm moving even after you hit the ball. It's kind of counter to what our instincts tell us to do, but it really makes a difference as your coach will insist. And here's why. When you follow through, essentially what you're doing is you're taking that force and you're applying for a greater amount of time. So if you didn't follow through, you'd apply a force for a small amount of time and you get a certain amount of change in the velocity and therefore momentum of the object. So you would get delta mv, it wouldn't be that big of a delta in your mv. However, if I apply the same force, but I follow through and apply it for a longer time, I'll get a larger change of velocity and therefore a larger change of momentum. And since the faster the ball is going, the more likely it is to be a home run. It's pretty important to follow through. All right. Now we can turn this around and look at it another way. All right. So we use this to protect ourselves from harm all the time. So let's think about this. I think most of us understand that it might be okay to dive into, say, a swimming pool full of water as long as it's deep enough, but it's probably not a good idea to dive into an empty swimming pool. Okay. Now, why is that? Well, it hurts more, right? But there's a reason why it hurts more. let's think about this. So in both cases, your momentum is going to go to zero. You have a very fixed delta mv, assuming you're falling from the same height in both cases. However, what you're changing is the amount of time across which that force is being applied. So if I dive into water, I'm going to change my momentum over a longer period of time, and therefore I'm going to be applying less force to my body. On the other hand, if I jump into concrete, I'm going to apply force for a very small amount of time, and therefore it's going to be a much larger force to achieve that same change in my momentum, bringing it to zero from whatever that initial value was. And there's millions of examples of that we're going to look into, like say airbags in cars, trampolines. There's just so many. There's so many cases of this. Now, since force is a vector quantity, that means impulse is also a vector quantity, right? Because force times time times the scalar, force is a vector, it's going to be a vector quantity. So that means direction matters. And here's a place you might get tripped up. So you got to always remember that force has a positive and negative direction. So look at this. I've got a 4 kilogram object moving at 5 meters per second in the positive direction. It has positive 20 kilograms meters per second of momentum. Now, if I apply a 10 Newton force in the negative direction for 6 seconds, F times T, negative 10 times 6 gives me negative 60 units of momentum change, of impulse. So I had 20 minus 60, I end up with negative 40 is my new momentum. All right, because I had a change of 60 momentum units, negative 60. Now I'm going to do the same thing. We're going to start with the same object. It's got 4 kilograms, 5 meters per second. It's got 20 kilograms meters per second of momentum to start with. I'm going to apply the 10 newtons of force, but this time I'm going to apply it in the same direction the object is moving, the positive direction. Well, now I have 10 times 60, but it's positive. So I'm going to add 60 to 20. I'm going to end up with 80. Right? Not a hard idea, but you've got to keep this in mind. But you've always got to analyze forces. And that's why we do free body diagrams early in the year. So we just got to get ourselves used to thinking which is the actual direction this force is acting, because that's going to inform us as to what type of change in momentum to expect that force to impose on the object that it's applying to. Okay, so let's just look at, say, stopping a car. Okay, so I have a car that's traveling 20 meters per second. It's a 500 kilogram car. And when I hit the brakes for 3 seconds, they're going to apply an average force of 2,000 newtons. So I have 2,000 newtons acting for 3 seconds. What I want to know is how fast the car ended up going. So let's just try this here. I'm going to start with impulse equals change in momentum. I'm going to write it. I'm going to expand it this way because remember, delta V always means final minus initial. So this is an expansion you got to get used to in this particular unit. So I'm going to say, well, the car is traveling in one direction, let's say the right, and the force is definitely in the opposite direction. Brakes don't make it go faster. So they're always acting in the negative direction if we assume the initial direction of the car is positive. And so therefore, I'm going to say I have negative 2,000 newtons times 3 seconds is going to equal the mass of the car times its final velocity minus its initial velocity. And when I solve this, I find the car is going 8 meters per second. And that makes sense, right? It's slowing down. Well, often there's more than one force acting on an object. So if you remember, it's better to think of Newton's second law instead of F equals ma as the sum of the F equals ma. Well, the same thing is going to be true here. The sum of the forces times time is basically the net impulse is going to equal the change in the object's momentum. So let's look at this here. I've got a rocket, which I think I drew a pretty cool rocket here myself. Okay, I have a rocket. Let's see. In this case, I know I have this. There's an upward thrust force that the engines are producing that's 350 newtons. We'll say that's in the positive direction, okay, because that's the direction it wants to move. Well, mg is pulling it downwards with 200, and there's a drag force of 50 newtons. So I want to figure out, how much is this thing going to change its force? So if this is 200 newtons, that means it's a 20 kilogram rocket. And let's just say it was initially moving upwards at 500 meters per, not 500, at 50 meters per second, and it's experiencing the same thrust force, drag force, and gravitational force as before. What I want to know is, well, how fast is it going to be moving 4 seconds later? So if these conditions exist for 4 seconds, what's the new velocity of this rocket going to be? So I'm going to say the sum of the forces times time is equal to the change in momentum. So the sum of the forces would be 350 in the positive direction, the direction we're trying to go, the direction we're moving, minus 200 because it's working in the opposite direction, minus 50 because drag is working in the opposite direction, equals the mass of the rocket times VF minus VI, and VI was 50. And so I put these in, I solve for it. I'm going to get 70 meters per second. So it makes sense. In those 4 seconds, I went from 50 to 70. Right? Now let's look at this. Let's look at how we can use force versus time graphs to figure out changes in an object's velocity or momentum. And so if you think about it, force times time is going to be equal to the impulse, right? To the change in momentum. So when I have a force graph, and you think about log pro, we're always doing force versus time graphs. Well, it tells me basically if I take the area under the line, if I integrate that, it's going to tell me what the impulse is, what the change in momentum is. So in this case here, I have a force of 2 newtons acting for 15 seconds. Well, 2 times 15, that means I have 30 units of momentum changes, a positive change of 30 kilogram meters per second. Or in this case, I could say Newton seconds, but it works out to be the same thing as kilograms meters per second. So weird. Okay, well, let's look at this one here. So let's just say I have this problem. I have a 5 kilogram cart initially going 1 meter per second in the negative direction. Okay, so it's going in the negative direction, 1 meters per second. When a force is applied to it over time, as shown below, it's a non-uniform force. I wonder how fast and which way is the car end up going afterwards. College Board loves to ask this question. All right. Well, let's just try this here. Okay. So the first thing I have to say is, okay, this is a change of momentum problem. I have a force versus time graph. So if I integrate the area into that line, it is going to tell me force times time, and force times time is impulse, which is change of momentum. So if I want to find this area here, remember, you don't go all the way down to the bottom of the graph, you go to 0. Okay. It's between the line and 0 always. So I'd say, well, I've got basically 4 newtons over 10 seconds, but I've only got half that area. So I'm going to say 4 times 10 divided by 2. That's the force times time part of this that I got off the graph. And that equals the 5 kilogram cart. I'm trying to find its final velocity, but it's going to be final minus initial, and its initial velocity was -1. So if I just clean this up a little bit, I get 20 equals 5 VF plus 5. And then when I solve for VF, I see it's going 3. So it was going in the negative direction at 1, and I was going in the positive direction at 3. All right, if I look at this, the question I've been asked is, how much did the momentum of the object change over the course of the 15 seconds shown? So this is just basically, can you find impulse? First of all, do you understand that impulse is change in momentum, and that it is also equal to force times time, and that can be found by integrating a force versus time graph, okay? So here you go. I've got a positive change of this, right? So I'm going to say, well, this is 4 times 5, but it's divided by 2. So 4 times 5 divided by 2. Plus, I've got 4 times another 5, but I don't have to divide that one by 2. And then after that, I have -2 times 5. So if I add all this up, what I get is 20 Newton seconds, or the same thing as 20 kilograms meters per second. So it's a positive change in its momentum. And that's it. We got a lot of fun with this. I think you're going to enjoy tomorrow's lesson. So see you. Thanks for watching.